Welcome to this problem walkthrough. In this session, we'll explore problem number 1150, check if a number is majority element in a sorted array. We'll discuss the problem statement, break down a few approaches, and analyze their complexities. Let's dive in and solve this step by step. In this problem, we are tasked with determining whether a given number, called the target, is a majority element in a sorted array of integers. A number qualifies as a majority element if it appears more than half the length of the array, denoted as n/2. The input includes two components, nums, which is a sorted array of integers in non-decreasing order, and target, the integer we want to evaluate. The output is a Boolean value, true if the target satisfies the majority condition, and false otherwise. This setup ensures that we focus on counting the occurrences of target efficiently within the context of a sorted array. To understand the problem more clearly, let's look at the first example. We have the input array nums equals 2, 4, 4, 4, 6, 6, 8, and the target is 4. The length of the array is 7, which means n/2 equals 3.5. Now, the number 4 appears 3 times in the array. Since 3 is greater than 3.5, target does not meet the majority condition, so the output is false. This example demonstrates how we calculate the majority threshold and compare it to the count of the target. Next, consider another example where nums equals 1, 2, 3, 3, 3, 3, 10, and the target is 3. Again, the length of the array is 7, so n/2 equals 3.5. This time, the integer 3 appears 4 times in the array, which is greater than 3.5. Therefore, the output is true. This shows that when a number's count exceeds the n/2 threshold, it qualifies as a majority element. Additionally, it highlights the importance of accurately counting the occurrences of target in the array. Now, we have another example with nums equals 1, 1, 2, 3, 4, 5, 6, and the target is 1. Here, the length of the array remains 7, so n/2 equals 3.5. The number 1 appears only 2 times in the array, which is less than 3.5. As a result, the output is false. This example emphasizes that even if a target appears multiple times, it must surpass the majority threshold to be considered a majority element. The constraints also remind us that the array is always sorted, which allows us to use efficient techniques to solve the problem. Lastly, it's important to note that if the target does not appear in the array at all, the output is automatically false. This is because a number with 0 occurrences cannot possibly meet the majority condition. The sorted nature of the array allows us to utilize binary search techniques to quickly determine whether target is present and, if so, count its occurrences efficiently. This observation is key to designing an optimal solution for the problem. To check if a number is a majority element in a sorted array, let's start by discussing two possible approaches. The first is the brute force approach. Here, the key idea is straightforward: count the occurrences of the target element in the array and compare this count to half the length of the array, n/2. To achieve this, you traverse the array once, keeping account of how many times the target appears. While this method is simple and requires no extra space, it has a significant drawback. It doesn't take advantage of the fact that the array is sorted, which means we're performing more computation than necessary. This leads us to a more efficient solution, the binary search approach. By leveraging the sorted nature of the array, we can locate the first and last occurrences of the target element using binary search. These indices allow us to calculate the target's count efficiently, avoiding a full traversal. This is because, in a sorted array, all instances of the target will appear consecutively, so the count is simply the difference between the last and first indices, plus 1. If this count is greater than n/2, the target is a majority element. This approach is faster and more aligned with the problem's constraints. To implement the binary search approach, we follow a series of steps. First, we perform a binary search to find the index of the first occurrence of the target. Then, we use binary search again to find the last occurrence of the target. With these two indices, we can calculate the count of the target as the difference between the last index and the first index, plus 1. The final step is to check if this count exceeds half the length of the array, n/2. The efficiency of this method comes from the fact that binary search operates in logarithmic time, so finding the first and last occurrences of the target is significantly faster than traversing the entire array. While this approach is highly efficient, it does have a drawback. Implementing binary search twice can make the code more complex compared to simpler methods. To address this, we can explore an optimized version of the binary search approach. This version focuses on the observation that, in a sorted array, if the target is a majority element, it must appear at the majority index, which is the element at n/2. Instead of locating both the first and last occurrences, we directly verify if the element at this index is the target. If it is, we confirm the majority condition by counting from the first occurrence of the target. This optimization reduces the number of binary searches required, but it introduces additional logical checks. The optimized binary search approach simplifies the process further and maintains a logarithmic time complexity. However, it assumes a solid understanding of binary search, and verifying the majority condition can become tricky due to potential edge cases. After evaluating these methods, we chose the standard binary search approach as our strategy for solving this problem. This approach strikes the best balance between efficiency and clarity. By leveraging the sorted property of the array, we minimize computation and achieve a logarithmic runtime, which is ideal for handling large inputs. Using the first and last indices to calculate the target's count ensures accuracy while keeping the implementation straightforward. Although the brute force method is easier to implement, it is less efficient and doesn't utilize the sorted nature of the array. On the other hand, while the optimized binary search approach offers slight performance improvements, it introduces complexity that may not be necessary for most use cases. Ultimately, the standard binary search approach provides the best trade-off, combining efficiency, scalability, and simplicity to solve the problem effectively. Here, the goal is to determine if a given integer, referred to as the target, qualifies as a majority element within a sorted array. A majority element is defined as an element that appears more than half the length of the array, or n/2 times. For example, in an array of size 5, a majority element would need to appear at least 3 times. To solve this, we can start with the brute force approach. This straightforward method involves counting how many times the target appears in the array and then comparing that count to the majority threshold. First, we initialize a count variable to 0, which will serve as our counter for the occurrences of the target. Next, we traverse the array using a loop, checking if each element matches the target. When a match is found, we increment the count by 1. This ensures we are correctly tracking the number of times the target appears in the array. Once we traverse the entire array, the next step is to compare the count with the majority threshold, which is n/2. If the count exceeds this threshold, we can confidently return true since the target is a majority element. Otherwise, we return false. Let's walk through an example to see this in action. Consider the input array ARR equals 2, 2, 1, 2, 2, and target equals 2. We start with count equals 0. As we iterate through the array, we compare each element to the target. The first 2 elements are 2, so we increment count to 2. The next element is 1, so the count remains unchanged. The final 2 elements are 2, and each match increments the count until it reaches 4. Finally, we compare count equals 4 with n/2 equals 2.5. Since 4 is greater than 2.5, we return true, confirming that 2 is the majority element in this array. There are a few key insights to consider when analyzing this problem. First, the definition of a majority element is critical. It must appear more than n/2 times in the array. For instance, in an array of length 5, this threshold is 3 occurrences. Second, the brute force approach has a time complexity of O(n), as we only need to traverse the array once, and a space complexity of O(1), since we only use a single variable to track the count. Additionally, we need to account for edge cases. If the array is empty, meaning n equals 0, the result is always false because no element can meet the majority element condition. If the target is not present in the array, the result is also false. Finally, in cases where all elements are the same, the result depends on whether the target matches the repeated value. These insights help ensure the solution is robust and handles all scenarios effectively. The problem relies on 2 simple data structures. First, the array itself, which contains the integers we need to analyze. The algorithm processes this array linearly, visiting each element exactly once. Second, we use a count variable to keep track of how many times the target appears. This single variable is efficient in terms of space, as it eliminates the need for auxiliary data structures like hash maps or frequency tables. By using just the array and a counter, we maintain a minimal memory footprint while achieving the desired result. The solution hinges on a few key operations. The first is the comparison operation, denoted by equals. This allows us to check if each element in the array matches the target, and only when this condition is true do we increment the count. The second crucial step is the threshold comparison, where we evaluate whether the count exceeds n/2. This guarantees that the target meets the definition of a majority element. Finally, the algorithm's efficiency comes from its single traversal of the array, which ensures an O(n) time complexity. While this is efficient for small to medium-sized arrays, it's important to note that performance could become a consideration for extremely large datasets. Nonetheless, the straightforward nature of this approach makes it a solid solution for the problem. This implementation solves the problem by leveraging the collections counter class to efficiently count the occurrences of each element in the input list nums. First, we create a counter object, which automatically counts and stores the frequency of each element in the array. Next, we check if the target element exists in the counter and whether its count is greater than half the length of the array, len nums:\/\/2. If both conditions are met, the function returns true, otherwise, it returns false. This approach is straightforward and efficient for small to medium-sized arrays, but it does include the cost of building the count dictionary. The overall time complexity is O(n), where n is the length of the input array, as counting the elements requires a single traversal of the array. The space complexity is also O(n), due to the storage of counts in the counter object. This is the Java implementation of LeetCode problem number 1150. Check if a number is majority element in a sorted array. The solution mirrors the Python logic, using a hash map to count occurrences of each number in the array and then checking if the target's count exceeds half the array's length. Key differences include Java's explicit type declarations, the use of a hash map instead of Python's counter, and Java's idiomatic methods for accessing and updating collections. In this problem, we are tasked with determining if a given number, called the target, is a majority element within a sorted array. A majority element is an element that appears more than half the number of times in the array. This means the count of the target must exceed the value of the array length divided by 2, specifically len nums:\/\/2. To solve this, we use the counter class from Python's collections module to count the occurrences of each element in the array. Then, we simply check if the target exists in the counter and if its count is greater than len nums:\/\/2. If both conditions are true, the function returns true, otherwise, it returns false. Let's now explore how this solution works with some examples to understand it better. First, consider the input nums=2, 3, 3, 3, 3, 4, 5, and target=3. The function begins by counting the occurrences of each element in the array, which results in a counter object, 2, 1, 3, 4, 4, 1, 5, 1. Next, the function retrieves the count of the target, which is 4, and calculates len nums:\/\/2, which is 3 since the array length is 7. The comparison step checks whether 4 is greater than 3. Because this condition is true, the target 3 qualifies as a majority element. Therefore, the function returns true. Now, for the second example, consider nums=1, 1, 2, 2, 2, 3, 4, with target=2. Counting the elements gives 1, 2, 2, 3, 3, 1, 4, 1. The count of 2 is 3, and again, len nums:\/\/2 is 3 since the array length is 7. This time, the count of 2 is not greater than 3, meaning the target does not satisfy the majority condition. So, the function returns false in this case. Now, let's analyze the third example where nums=1, 1, 1, 1, 2, 3, 3, and target=1. The function starts by counting the elements, resulting in 1, 4, 2, 1, 3, 2. The count of the target 1 is 4, and the array length is 7, so len nums:\/\/2 is 3. The comparison checks whether 4 is greater than 3. Since this condition holds true, the target 1 is confirmed as a majority element. The function returns true in this case. To summarize the key points, the counter object allows us to count the occurrences of each element in linear time, making the solution efficient. The majority condition counts, target, len, nums, // 2 ensures we only return true when the target appears more than half the length of the array. The solution also gracefully handles edge cases, such as when the target is not present in the array, by defaulting the count to 0. These examples demonstrate that the solution is both correct and efficient. The use of the counter class ensures that we can count elements in O, N, time, and the straightforward comparison logic makes the solution easy to understand and implement. By verifying the count of the target against the majority condition, we can confidently determine if the target is a majority element in the array. This approach is not only effective but also handles edge cases seamlessly, making it a robust solution to the problem. Here, we analyze the time complexity of the provided solution. The first step involves counting the frequency of each element in the input list nums using the counter class from the collections module. This operation requires iterating through the entire array once, making it an O(n) operation, where n is the length of the array. Next, accessing the count of the target element in the counter object is a dictionary lookup. On average, dictionary lookups have a constant time complexity of O(1). Finally, the comparison step checks if the count of the target is greater than half the length of the array. This involves accessing the array's length, which is O(1), and performing a single comparison, which is also O(1). When combining these steps, the counting operation dominates the overall time complexity, resulting in O(n). Now, let's evaluate the space complexity of the solution. The primary contributor to space usage is the counter object, which stores the frequency counts of each unique element in the array. In the worst-case scenario, where all elements in nums are unique, the number of keys in the counter object equals the number of elements in the array. If we let k represent the number of unique elements, the space required for the counter object is OK. Additionally, the function uses a constant amount of space for variables like counts and the result of the comparison, which contributes O(1). In the worst case, when every element in the array is unique, k becomes equal to n, making the overall space complexity O(n). Let's compare this approach to other alternatives. A naive solution would involve manually iterating through the array to count the occurrences of the target element. This approach performs a single traversal, resulting in an O(n) time complexity, and uses only O(1) space since no additional data structures are required. However, while the space complexity is better, the time complexity remains the same as the current solution. An optimized approach could take advantage of the fact that the input array is sorted. By using binary search, we can identify the first and last occurrences of the target element in O log n time. The total count of the target can then be computed as the difference between these indices plus 1. This method reduces the time complexity to O log n and the space complexity to O(1). To summarize, the current solution has a time complexity of O(n) and a space complexity of O(n), which is efficient for smaller inputs. However, for larger, sorted arrays, leveraging binary search offers significant performance improvements, especially when optimizing for time and space constraints. Let's start by looking at some common mistakes that can arise when solving this problem. One frequent issue is neglecting edge cases, such as arrays that are empty or contain only a single element. This happens because many algorithms assume the input array will have enough elements to determine a majority, which isn't always true. To avoid this, you should explicitly handle arrays of size 0 or 1 before diving into the main logic. Another mistake involves using n/2 in a way that leads to floating point division in some languages, such as Python. If your comparison logic relies on integer values, this subtle bug can produce incorrect results. To fix it, use integer division, like n/2 in Python, or make sure to explicitly cast the result to an integer in other languages. Lastly, inefficiency in counting elements can also be problematic. For example, counting the occurrences of the target multiple times within a loop can lead to O(n²) runtime. Instead, aim for a single pass or preprocess your counts using a hash map to keep your solution efficient. Now, let's discuss some other pitfalls. An incorrect implementation of the Boyer-Moore voting algorithm is a notable one. This algorithm is efficient, but it's easy to misunderstand the elimination process or forget to verify the candidate after selection. Without this verification step, false positives can occur. To avoid this, always perform a second pass to confirm that your candidate truly appears more than n/2 times. Another common misunderstanding is misinterpreting the requirement for a majority element. Simply assuming any element can be a majority without explicitly checking its count will lead to errors. To ensure correctness, always validate that the element satisfies the majority condition by counting its occurrences and comparing against the threshold. Next, let's consider some insights that can help during interviews. This problem is a great example of leveraging linear scans and space optimizations. Algorithms like the Boyer-Moore voting algorithm are frequently asked because they showcase how to achieve constant space efficiency. While brute force approaches, such as counting or using hash maps, are easier to understand, they're best suited for smaller arrays. If you choose this approach, make sure to discuss its trade-offs in terms of time and space complexity. It's also important to address edge cases during your explanation, such as arrays with no majority element, arrays with duplicates, or arrays where all elements are identical. If the array is sorted, you can further optimize the solution by using binary search to count occurrences in O, log n, time, rather than scanning the entire array. This problem is often included in interviews because it tests fundamental concepts like counting strategies, hash maps, and space-efficient algorithms. To solidify your understanding, it's helpful to explore related problems that build on similar principles. For instance, LeetCode Problem 169, Majority Element, focuses on finding an element that appears more than half the time in an unsorted array. Another extension is Problem 229, Majority Element 2, which requires identifying all elements that appear more than n/3 times. Of course, there's the current problem, Problem 1150, where the array is sorted, adding a unique twist. Finally, Problem 1696, Jump Game 6, while not directly related to majority elements, involves optimization techniques and edge case handling, which are transferable skills. Studying these problems will deepen your understanding of counting, optimization, and handling edge cases effectively. Finally, let's explore alternative approaches to solving this problem. The hash map approach is straightforward. Use a dictionary to count the occurrences of each element, and then check if any element exceeds n/2. This method runs in O, n, time but requires O, n, space due to the dictionary. Alternatively, you can use the sorting approach, where sorting the array ensures that the majority element, if it exists, will always be in the middle. This method has a time complexity of O, n log n, and uses O, 1, space, but it's less efficient than linear time algorithms. The Boyer-Moore voting algorithm is another option. It identifies a candidate in a single pass using a voting mechanism and then confirms it in a second pass. This is optimal in both time and space, with O, n, time and O, 1, space complexity, but it's more challenging to implement without errors. Choose an approach that aligns with the problem's constraints, the size of the array, and the characteristics of the input you expect. Great job following through this problem. Today, we learned how to approach problem number 1150 and discussed both brute force and optimization techniques. Keep practicing to solidify your skills, and remember to utilize array properties for efficiency. Thanks for watching, see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!